My name is Konstantin Keil. I'm a PhD student at the University of Giessen, and I'm going to talk about a little bit about the set tests at our facilities, going a little bit about the physics and the history behind the ion thrusters. So I think in the end, it's a good mixture of basics for the ones who are new in the field, and at the end also some a nice measurement technique that might also be new to the ones that are more familiar with this field and are already some years into electric propulsion. So first of all, I just want to quickly talk a little bit or lose some words about the university, so you know where we're located. I come from the Justus-Liebig University in Giessen, which is in the middle of Germany. It is quite an old university, founded 1607, and has around 11 departments concerning fields like medicine or law school and also physics. And within this physics field, we also do have a specialized course of study concerning electric propulsion. And what's really special about this study course is that normally the study courses about aeronautics and astronautics are mainly focused on mechanical engineering, and that's something special here on this side, which is more focused on electrical engineering, especially tailored for the field of electric propulsion. And our focus on electric propulsion comes from our history, because the radio frequency ion thruster, which is the RIT2X we talk about here, or what was the subject of all the tests in this whole project, was invented, or RIT technology was invented by Professor Liebig in the 60s in Giessen, and led in this time the ion thrusters research group, which is now under leadership of Professor Keil. And we broadened a little bit more our field, not going into the thruster itself, but also looking for alternative propellants, diagnostics, neutralizers, electromagnetic compatibility, and also simulation. And therefore, Christoph already talked a little bit about the principle of an RF ion thruster, so I don't want to go much into detail. Maybe I just want to underline why it is in some parts maybe beneficial to use electric propulsion over chemical propulsion. As a key message is because we don't rely on chemical reactions that accelerate our propulsion, our propellant out of the thruster, but instead we decouple it, the ionization of our propellant and the acceleration, which makes it feasible to reach higher exhaust velocities and therefore higher ISPs, which might be beneficial for special types of missions, as a key take-home message. And now I want to go more into the tests that were performed at our premises. And we do have a lot of vacuum facilities for different needs. You can see them here on the screen. But for the test, we went into our biggest vacuum facility. It's this one. It's the Jumbo. Jumbo, the name says it all. It is the biggest facility we have in Giessen. And as it was commissioned late in the 60s, it was also the biggest facility in Europe. That's now not the case. You will hear about bigger facilities in the next presentation. But we still used it for this test, and with the given parameters you can see here, it was still feasible to run the RIT2X in this test facility, and also to achieve the desired background pressures that was needed to perform good tests and to get reliable results with the thruster. So let's have a look more on the test setup. It was already said by Christoph that we, in our case, used ground support equipment. In a special case, a test power supply. You can see it here. So basically, these are lots of voltage supplies that was especially chosen for the test with the RIT2X to fulfill all the needs. We also came up with a fluid management system, or let's more or less call it a flowboard, which is built up of some valves and mass flow controllers to feed the desired propellant flow into the thruster via computer and tweak a little bit here on the parameters. And all of this is then controlled via C and a software. We programmed this software especially for this test and all the needs for the test. So we also incorporated red line warnings, for example, so that we had automatic shutdown procedures in case of somehow the pressure in the vacuum facility rose to a critical level, or in case of a propellant might stop to flow into the neutralizer and things like that. This was handled with the software, so it was safe to operate, and we were we could fight every possible scenarios that might do a failure, but there wasn't no failure, so we didn't need it, but it was there in case it was needed. And also what we also need for a good test are some auxiliary things that were already there, like the propellant itself, or for example, a beam gun. So a device that's in the test facility to stop the ion beam that comes out of the thruster, which has also to handle this power that comes that is in the beam of the ion thruster. So now talking a little bit about the measurements we conducted in Giessen. These were mainly two things. One is a Faraday array measurement. We'll hear more details in the next presentations. So I don't want to go much into detail. Just to let you know, we use this device to measure the spatial distribution of the ion beam to calculate, for example, the beam divergence of the thruster. And what you can keep in mind in comparison for the next presentation, we have, in our case, our Faraday array runs in a Cartesian coordinate system through the beam. This is a little bit different than to the measurement that was performed here at Aerospatio. So keep that in mind, and you see the difference. But if you calculate or do the right math to correct for that, you can get the same results. At the end, I want to close with a very neat measurement that was used during this measurement campaign. It was set up from my colleague Daniel Anders from the optics research group. And this very interesting experiment allowed us to measure the intergrid distance of the thruster. And how was this done? You can see it here in my mouse if I move slowly. So the basic principle is the following. We have here a laser emitting very short laser pulses in the infrared light. These short infrared pulses get then frequency doubled to generate green light, because the camera or the detector we're using for the laser light, the street camera, is more is optimized for visible light. And then we filter out parts of the light that didn't get frequency doubled to trigger the street camera. So what happens then with this green laser light? We split the beam into two directions. One here in the beam block, and the other way goes here into in the direction of the thruster into the grid assembly. And what happens in the grid assembly and in the beam block? The laser beam hits the grid or the beam block and gets scattered there. And the scattered light travels back and goes here into the street camera. And we get three three responses, one from the beam block, one from first grid, and one of the second grid of the thruster. And the street camera is a device that allows us to take very precise temporal measurements of these of this light. And now, if we have here on the right this fixed length where the laser light travels, we are able to perform absolute measurements in comparison to this length and see if the thruster itself moves and also if the distance between these grids also changes. So talking about that, that's all I wanted to talk right now about. I hope you found it interesting, and I hand over to my colleague Simone for the next topic. Thank you.